Hello everyone, this video is for week 9, topic 8, part 1, Introduction to Logarithms. And this topic can be found on your modules on pages 112 to 117, and we'll be discussing examples 1 to 4. For the lesson outline, we have first, logarithms and its inverse relationship with exponents. Second, exponential and logarithmic forms of an equation. And third, real-life situations that can be represented by logarithmic functions. So let us start with the logarithm concept. So think of a logarithm of x to the base b, denoted by this, as the exponent of b that gives x. Okay, so again, this is read as logarithm of x to the base b. So ask yourself, what would be the exponent of b so that we can have the value of x? Okay, so think of that. Now let us have some examples. First, we have logarithm of 81 to the base 3. So what would be the exponent of 3 so that we can have 81? Okay, so that number would be 4 because 3 raised to 4 is equal to 81. Or in other words, to get 81, 4 must be the exponent of 3. Such that we have logarithm of 81 to the base 3 is equal to 4. Next example, we have logarithm of 32 to the base 2. So ask yourself, what would be the exponent of 2 so that we can have 32? So that number would be 5 because 2 raised to 5 is equal to 32. Or 5 must be the exponent of 2 so that we can have 32. Next, we have logarithm of 1 to the base 5. Okay, so if you can still remember the laws of exponents, one of the laws says any number except 0 raised to 0 is always equal to 1, and therefore the exponent of 5 so that we can have 1 is 0. Okay, so therefore we have logarithm of 1 to the base 5 is equal to 0. And we have logarithm of 1/6 to the base 6. So remember, this is fraction and our base is a whole number. So how is it possible to have a fraction if we have the base as a whole number? Okay, so that would be possible if your exponent is negative. So think of the laws of exponents when you have a negative exponent. So to get 1/6, your 6 must be raised to negative 1. Okay, so we have 6 raised to negative 1 is equal to 1/6. So remember the laws of exponents that we have discussed in the earlier tutorial videos that we had. Okay, and therefore we have logarithm of 1/6 to the base 6 is equal to negative 1. Now let us discuss example number 1. Without using a calculator, find the value of the following logarithmic expressions. Number 1, logarithm of 64 to the base 2 is equal to what? Okay, ask yourself, what exponent of 2 will give 64? What do you think? Okay, so the answer is 6. And therefore, we have logarithm of 64 to the base 2 is equal to 6. Number 2, we have logarithm of 729 to the base 9. So, what exponent of 9 will give 729? What do you think? So the answer is 3. Okay? So we have logarithm of 729 to the base 9 is equal to 3. Number 3, logarithm of 5 to the base 5. What exponent of 5 will give 5? So this is very easy. And the answer is, of course, we have 1. So logarithm of 5 to the base 5 is equal to 1. Now let us proceed to number 4, logarithm of 16 to the base 1 half. What exponent of 1 half will give 16? So our base is 1 half. This can be expressed as 2 raised to negative 1, applying the laws of exponents, which is the negative law of exponent. So 2 raised to negative 1 must be raised to what for us to have 16? That would be negative 4. So 2 raised to negative 1 raised to negative 4 is equal to 2 raised to positive 4, and that is equal to 16. And therefore, logarithm of 16 to the base 1 half is equal to negative 4. Now we have number 5, logarithm of 1 to the base 7. So what exponent of 7 will give 1? So again, we'll be using one of the laws of exponents, which is the 0 exponent. So we have 0. Okay, so logarithm of 1 to the base 7 is equal to 0. And the last one, we have example number 6. We have logarithm of 1 over square root of 5 to the base 5. What exponent of 5 will give? Uh, 1 over square root of 5. What do you think? So let us see. Okay, we have logarithm of 1 over square root of 5 to the base 5. So let us simplify this part. So 1 over square root of 5 is equal to 1 over 5 raised to 1 half. If you can still remember, we have this radical. This radical can be expressed as a number with a rational exponent. So this is your index, which is 2. The exponent of 5 is 1. So 1 is the numerator and the index is the denominator. So we have square root of 5 can be expressed as 5 raised to 1 half. And this one can be expressed using the laws of exponent. 1 over 5 raised to 1 half can be expressed as 5 raised to negative 1 half. Okay? So we can substitute 5 raised to negative 1 half to this 1 over square root of 5. Okay? So looking at this logarithm of 5 raised to negative 1 half to the base 5. What do you think is the answer? What would be the exponent of 5 so that we can get 5 raised to negative 1 half? So of course, that would be negative 1 half. Okay? So the answer for this is negative 1 half. Now let us discuss the definition of logarithm of a with base b. Let a and b be positive real numbers such that b is not equal to 1. The logarithm of a with base b, denoted by this, is defined as the number such that b raised to logarithm of a to the base b is equal to a. That is, logarithm of a to the base b is the exponent that b must be raised to produce a. Logarithms and exponents allow us to express the same relationship in two different ways. The following table shows how the expressions in example 1 can be written using two equivalent forms. So we have here for the first column logarithmic form, and for the second column we have exponential form. For number 1, we have logarithm of 64 to the base 2 is equal to 6. So these can be expressed as exponential form as 2 raised to 6 is equal to 64. So remember, we have 2 as the base, and to get 64, 2 must be raised to 6. So that is why we have 2 raised to 6 is equal to 64. For number 2, we have logarithm of 729 to the base 9 is equal to 3. So we have the base 9, and the exponent of 9 to get 729 is 3. And therefore, this can be written in exponential form as 9 cubed is equal to 729. For number 3, we have logarithm of 5 to the base 5 is equal to 1. So we have the base 5, and its exponent is 1 to get 5. So the answer is, for exponential form, we have 5 raised to 1 is equal to 5. Next, we have number 4, logarithm of 16 to the base 1/2 is equal to negative 4. So what do you think? What is its exponential form? Okay, so the answer is 1/2 raised to negative 4 is equal to 16. For number 5, we have logarithm of 1 to the base 7 is equal to 0. So let us see if you can answer this. What do you think is the exponential form of this? Okay, so we have the base 7, the exponent is 0 to get 1. So we have 7 raised to 0 is equal to 1. And for number 6, we have logarithm of 1 over square root of 5 to the base 5 is equal to negative 1/2. So let us see if you can answer its exponential form. Okay, so we have the base 5. Its exponent is negative 1/2 to get 1 over square root of 5. And therefore, we have its exponential form is 5 raised to negative 1/2 is equal to 1 over square root of 5. Exponential and logarithmic forms. Logarithmic form, we have logarithm of a to the base b is equal to c. And for the exponential form, we have b raised to c is equal to a. In both the logarithmic and exponential forms, b is the base. So for logarithmic form, b is the base, and for the exponential form, b is also the base. In the exponential form, c is an exponent, but c is equal to logarithm of a to the base b. This implies that the logarithm is actually an exponent. So for logarithmic form, c is the exponent of b so that we can have the value of a. And for the exponential form, c is also the exponent of b to get the value of a. In the logarithmic form, logarithm of a to the base b, a cannot be negative. Again, a cannot be negative. For example, logarithm of negative 8 to the base 2 is not defined, since 2 raised to any exponent will never result to a negative number. So you cannot find any number as the exponent of 2 to get negative 8. So again, a cannot be negative. And the value of the logarithm of x to the base b can be negative. Again, the value of logarithm of x to the base b can be negative. So in other words, the exponent of b can be negative to get the value of x. For example, logarithm of 1 over 125 to the base 5 is equal to negative 3, because 5 raised to negative 3 is equal to 1 over 125. So again, the value of logarithm of x to the base b can be negative. Let us now discuss the definition of common and natural logarithms. Common logarithms are logarithms with base 10. The base 10 is usually omitted when writing common logarithms. This means that logarithm of x is a short notation for logarithm of x to the base 10. The number e, which is approximately 2.71828, has important applications in mathematics. Logarithms with base e are called natural logarithms and are denoted by ln. In other words, ln x is another way of writing logarithm of x to the base e. For example, number 2, we write the following exponential equations in logarithmic form whenever possible. So we have here the first column for exponential form. For the second column, we have logarithmic form, and for the third column, we have for the notes intended for some concepts that need to be emphasized. So let us start with letter A. 5 cubed is equal to 125. So what do you think is its logarithmic form? Okay, so we have the answer is logarithm of 125 to the base 5 is equal to 3. So remember, the base is 5, 3 is the exponent, and the answer is 125. Letter B. 7 raised to negative 2 is equal to 1 over 49. So what do you think is its logarithmic form? Okay, so we have logarithm of 1 over 49 to the base 7 is equal to negative 2. So I would like to emphasize that it is right to have a negative exponent but not a negative base. So it's okay to have negative 2 as the exponent, but we can never have the base negative. Let us proceed to letter C. 10 squared is equal to 100. What do you think is its logarithmic form? So the answer is logarithm of 100 is equal to 2. So take a look at this. Our base is 10. So if we will be expressing this in logarithmic form, since our base is 10, this is called a common logarithm. Okay, so we have discussed that earlier, that when we have the base equal to 10, we usually omit that. Okay, so once the base is not written, it is understood that the base is 10. Okay, so but it is also correct to write logarithm of 100 to the base 10 is equal to 2. Okay, and letter D, we have 2/3 squared is equal to 4 over 9. And its logarithmic form is, we have logarithm of 4 over 9 to the base 2/3 is equal to 2. Okay, so again, I would like to emphasize that it is right to have a fractional or decimal base. So our base is fraction, so it is right to have a fractional or decimal base as long as it is positive. Okay, so the base must be always positive. Okay, so next we have letter E. 0.1 raised to negative 4 is equal to 10,000. What do you think is its logarithmic form? Okay, so this time we have decimal base. We have a negative exponent. So what do you think is its logarithmic form? The answer is logarithm of 10,000 to the base 0.1 is equal to negative 4. Letter F, 4 raised to 0 is equal to 1. What do you think is the answer for its logarithmic form? We have logarithm of 1 to the base 4 is equal to 0. Letter G, 7 raised to b is equal to 21. And its logarithmic form is, we have logarithm of 21 to the base 7 is equal to b. Letter H, e raised to 2 or e squared is equal to x. So remember, our base is e, which is called natural logarithm. So what do you think is the answer for the logarithmic form? We have ln x is equal to positive 2. Okay, so another way of writing this is logarithm of x to the base e is equal to 2. And for letter I, we have negative 2 raised to 2 or squared is equal to 4. What do you think is its logarithmic form? Okay, so it is not possible. Why? Because this exponential form cannot be written in logarithmic form since the base is negative. So we have emphasized that earlier that your base can never be negative. Okay? For example, number 3, we write the following logarithmic equations in exponential form. So we have here for the first column, we have logarithmic form, and for the second column, we have exponential form. So let us start with letter A. Logarithm of m is equal to n. So as you can see, your base is not written. So it means to say this is a common logarithm with the base 10. Okay, so it means to say our base is 10, the exponent is n, and the answer is m. So therefore its exponential form is 10 raised to n is equal to m. Letter B, logarithm of 81 to the base 3 is equal to 4. Okay, so for its exponential form, what do you think? Okay, so we have our base 3. The exponent is 4 and the answer is 81. So 3 raised to 4 is equal to 81. Letter C, logarithm of 5 to the base square root of 5 is equal to 2. So therefore, the exponential form of this is the square of square root of 5 is equal to 5. Letter D, logarithm of 64 over 27 to the base 3/4 is equal to negative 3. So its exponential form is, okay, so we have 3/4 raised to negative 3 is equal to 64 over 27. So I would like to emphasize this parenthesis. So the parenthesis must be used for the whole fraction. Okay, since the exponent negative 3 is the exponent of the fraction 3/4. So if there is no parenthesis, it means to say that the exponent negative 3 is only for positive 3. Okay, so take note of the use of these parentheses. Next, we have letter E, logarithm of 2 to the base 4 is equal to 1/2. Okay, so 4 is the base, the exponent is 1/2, and the answer is 2. So we have the answer 4 raised to 1/2 is equal to 2. For letter F, logarithm of 0.001 to the base 10 is equal to negative 3. Okay, so what do you think is its exponential form? So the answer is 10 raised to negative 3 is equal to 0.001, or we can also rewrite this as 10 raised to negative 3 is equal to 1 over 1000. Okay, so this one is decimal, in decimal form, and the other one is in fractional form. And for letter G, we have ln 8 is equal to A. So we have ln, it means to say this is a natural logarithm, and if we have natural logarithm, we use E as our base, or our base is E. Okay, so what do you think is exponential form? So remember, this is the exponent, this is the answer, and our base is E. So therefore, its exponential form is E raised to A is equal to 8. Okay? Sample application. The Richter scale. In 1935, Charles Richter proposed a logarithmic scale to measure the intensity of an earthquake. He defined the magnitude of an earthquake as a function of its amplitude on a standard seismograph. The following formula produces the same results, but it is based on the energy released by an earthquake. So we have earthquake magnitude on Richter scale. The magnitude R of an earthquake is given by R is equal to 2/3 times the logarithm of E over 10 raised to 4.40, where E in joules is the energy released by the earthquake. The quantity 10 raised to 4.40 is the energy released by a very small reference earthquake. Example number 4. Suppose that an earthquake released approximately 10 raised to 12 joules of energy. Letter A, what is its magnitude on a Richter scale? Letter B, how much more energy does this earthquake release than that by the reference earthquake? So let us first discuss the answer for the first question. So we have the given, the energy is equal to 10 raised to 12, and you are asked for the magnitude of on a Richter scale. So using the formula, we have r is equal to 2/3 times the logarithm of 10 raised to 12, which is the value of re, over the constant number 10 raised to 4.40. So in this case we have here, we just subtract the two exponents by applying the laws of exponents. Okay, we have the same base, so we need to subtract the two exponents. So we have r is equal to 2/3 times the logarithm of 10 raised to 7.6. So 12 minus 4.40 is 7.6. Okay, so in this case, this is a common logarithm, which means to say that the base is 10. Okay, so if you can still remember, in our definition of logarithm, so you need to think a logarithm of x to the base b, which is denoted by this logarithm of x to the base b, as the exponent of b that gives x. So looking at the given, we have our base is 10. So what do you think is the answer for the logarithm of 10 raised to 7.6, given that our base is 10? So what must be the exponent of 10 so that we can get 10 raised to 7.6? Of course, the answer is 7.6. And therefore, r is equal to 2/3 times 7.6, which is approximately 5.1. Okay, so this is the answer for question A. For question B, how much more energy does this earthquake release than that by the reference earthquake? So for the solution, we have this earthquake releases 10 raised to 12 over 10 raised to 4.40, which is equal to 10 raised to 7.6, which is approximately 39,810,717 times more energy than that by the reference earthquake. Okay, so this is the answer for question B. So for this video, we have discussed the definition of logarithm, the definition of common logarithm and natural logarithm, and we have also discussed the examples of each. And lastly, we have also discussed a sample application for this topic. Okay, so I hope you have learned something from this video tutorial, and we will be seeing each other in our next video tutorial. So thank you very much, and God bless.